For as long as humans have gazed upward at the night sky, we've asked fundamental questions. What is this vast cosmos we inhabit? How did it all begin? What laws govern the dance of galaxies, stars and planets? And perhaps most intriguingly, what is the ultimate fate of everything we can see and everything we cannot? This documentary will take you through the complete story of our universe, from its explosive birth to its potential ending, examining the elegant physical laws that orchestrate this cosmic symphony. We'll explore concepts that might seem impossibly complex, but I promise to break them down into ideas you can visualize and understand, using everyday analogies and clear language. Think of the universe as the ultimate machine, the grandest mechanism ever conceived. But unlike a machine built by human hands, the universe wasn't constructed according to a blueprint. Instead, it operates according to fundamental rules that emerged from the very fabric of reality itself. These rules, which we call the laws of physics, are surprisingly simple when you get to know them, yet they give rise to all the complexity and beauty we observe. Let's start at the very beginning, though I should warn you that beginning is a tricky word when it comes to the universe. About 13.8 billion years ago, something extraordinary happened. We call it the Big Bang, though that name is somewhat misleading because there was no explosion into empty space. Instead, space itself came into being, along with time, matter, and energy. Imagine trying to think about what existed before the Big Bang. It's a bit like asking what's north of the North Pole. The question itself doesn't quite make sense because time itself began with the Big Bang. There was no before because before requires time, and time hadn't started yet. In that first inconceivably brief instant, the entire observable universe, everything we can see with our most powerful telescopes, was compressed into a region far smaller than a single atom. The temperature was beyond anything we can easily comprehend, around 10 to the 32 degrees Kelvin. To put that in perspective, that's a 1 followed by 32 zeros. At such temperatures, matter as we know it couldn't exist. There were no atoms, no subatomic particles as we understand them today, just pure energy fluctuating wildly in what physicists call a quantum foam. Within the first tiny fraction of a second, something remarkable called cosmic inflation occurred. The universe expanded exponentially, growing from smaller than an atom to roughly the size of a grapefruit in less than 10 to the negative 32 seconds. That's a decimal point, followed by 31 zeros, and then a 1. This inflation was driven by a peculiar form of energy that physicists are still working to understand fully. Why did inflation happen? The best explanation involves quantum fields, which are like invisible fabrics that permeate all of space. One particular field, called the inflaton field, was in a high-energy state, and this energy drove space itself to expand at an incredible rate. Think of it like a rubber band being stretched, except the rubber band is space itself, and it's being stretched faster than the speed of light. This doesn't violate Einstein's rule that nothing can move faster than light through space, because space itself was doing the expanding. As the universe cooled during this first second, something magical happened. Energy began to condense into matter. This follows Einstein's famous relationship between energy and mass, which states that energy equals mass times the speed of light squared. Because the speed of light is such a large number, and we're squaring it, making it even larger, a tiny amount of mass represents an enormous amount of energy. Running this equation in reverse, energy can transform into mass when conditions are right. The first particles to form were quarks and gluons, the fundamental building blocks that would eventually combine to make protons and neutrons. At this stage, the universe was still incredibly hot, around 10 billion degrees Kelvin, too hot for these particles to stick together. The entire cosmos was essentially a thick soup of fundamental particles, bouncing off each other in the heat. As the universe continued to expand, it cooled, and after about 3 minutes, something crucial happened. The temperature dropped enough to around 1 billion degrees Kelvin for protons and neutrons to combine and form the first atomic nuclei. This process, called Big Bang nucleosynthesis, produced the lightest elements, hydrogen, helium, and trace amounts of lithium and beryllium. Here's where things get interesting. The ratio of hydrogen to helium that formed during these first few minutes was determined by the fundamental physics of nuclear reactions and the expansion rate of the universe. When we look at the oldest stars and gas clouds in the universe today, we find exactly the ratio of hydrogen to helium that our theories predict should have formed in the Big Bang. It's roughly 75% hydrogen and 25% helium by mass, and this cosmic agreement between theory and observation is one of the strongest pieces of evidence that our Big Bang model is correct. But the universe still wasn't transparent. For the next 380,000 years, it remained opaque, filled with the hot plasma where photons of light couldn't travel far before bouncing off free electrons. Imagine trying to see through a thick fog, except the fog fills all of space. Then, as the temperature dropped to around 3,000 degrees Kelvin, something beautiful occurred. Electrons combined with nuclei to form the first complete atoms, mostly hydrogen and helium. This event, called recombination, made the universe transparent for the first time. The light that was released at that moment has been traveling through space ever since, stretching and cooling as the universe expanded. Today, we detect it as the cosmic microwave background radiation, a faint glow coming from all directions in space, cooled to just 2.7 degrees above absolute zero. This ancient light is like a baby picture of the universe, showing us what the cosmos looked like when it was just a tiny fraction of its current age. Now that we've seen how matter came into being, let's explore the fundamental force that shapes the large-scale structure of the universe. Gravity. You might think of gravity as a force that pulls objects together, and that's not wrong, but it's not the deepest truth. Einstein revolutionized our understanding with his general theory of relativity, which revealed that gravity isn't really a force at all. Instead, it's the result of space-time itself being curved by the presence of matter and energy. This requires us to think about space and time in a new way. We're used to thinking of space as an empty stage where events unfold, and time as something separate that ticks away uniformly. But Einstein showed that space and time are woven together into a single four-dimensional fabric called spacetime. When you place a massive object in this fabric, it creates a depression, like placing a bowling ball on a stretched rubber sheet. Imagine you're rolling a marble across that rubber sheet. If the sheet is flat, the marble travels in a straight line. But if there's a bowling ball creating a depression, the marble's path curves as it rolls past, not because the bowling ball is pulling on it through some mysterious force, but because the marble is following the straightest possible path through the curved geometry of the sheet. This is exactly how planets orbit the Sun and how galaxies hold themselves together. They're following the geometry of curved space-time. The mathematical description of this curvature is captured in Einstein's field equations, which in words state that the curvature of space-time at any point is proportional to the energy and momentum of matter at that point. These equations are beautifully simple in concept, though working with them requires sophisticated mathematics. They tell us that matter tells space-time how to curve, and curved space-time tells matter how to move. One of the most profound consequences of relativity is that there's a cosmic speed limit. The speed of light, approximately 300 million meters per second. Nothing with mass can reach this speed, and information cannot travel faster than this through space. But why does this limit exist? The answer lies in the nature of space-time itself. As an object moves faster and faster, something strange happens. Time for that object begins to slow down relative to a stationary observer, and the object's mass appears to increase. These aren't illusions or measurement errors. They're real effects of how space-time works. As you approach the speed of light, time dilation and mass increase become more and more extreme. To actually reach the speed of light would require infinite energy, which is why it's impossible for anything with mass. Light itself, photons, can travel at this cosmic speed limit because they have no rest mass. From the perspective of a photon, if it could have a perspective, no time passes at all during its journey. A photon emitted from a distant galaxy billions of years ago experiences its entire journey to your eye as occurring in zero time. This speed limit has profound implications for the structure of the universe. It means there are regions of space so far away that light from them hasn't had time to reach us yet, even though the universe has been around for nearly 14 billion years. It creates what we call a cosmic horizon, a boundary beyond which we cannot see, not because there's nothing there, but because light from those regions hasn't had time to arrive. When gravity becomes extremely strong, space-time curvature reaches its extreme limit, creating black holes. These are perhaps the most bizarre and fascinating objects in the universe. A black hole forms when matter becomes so compressed that the curvature of space-time becomes infinite at a central point called a singularity. Let me help you understand what makes a black hole so special. Every massive object has what's called an escape velocity, the speed you'd need to completely escape its gravitational pull. For Earth, It's about 11 kilometers per second. For more massive objects, or objects of the same mass but smaller size, the escape velocity is higher. A black hole is an object where the escape velocity exceeds the speed of light. Since nothing can go faster than light, nothing that crosses a certain boundary, called the event horizon, can ever escape. The event horizon isn't a physical surface. If you were falling toward a black hole and crossed the event horizon, you wouldn't feel anything special at that moment. But from that point on, all possible paths through space-time lead inexorably inward toward the singularity. It's not that there's a strong force pulling you in. Rather, the geometry of space-time itself has become so warped that forward in time now points toward the center of the black hole. Black holes come in different sizes. Stellar mass black holes formed when massive stars collapse might have masses between 3 and a few dozen times the Sun's mass. Supermassive black holes found at the centers of most galaxies, including our own Milky Way, can have masses of millions or even billions of solar masses. These giants grow over cosmic time by consuming surrounding matter and merging with other black holes. Recent observations have confirmed stunning predictions of general relativity. When two black holes spiral into each other and merge, they create ripples in space-time itself, called gravitational waves, which travel outward at the speed of light. We've now detected dozens of these merger events, watching black holes and neutron stars collide billions of light-years away. Each detection confirms that Einstein's century-old equations correctly describe how space-time behaves even in these most extreme conditions. While general relativity describes the universe on large scales, there's another revolutionary theory that governs the behavior of matter and energy at the smallest scales: quantum mechanics. If relativity seems strange, quantum mechanics is utterly bizarre, challenging our most basic intuitions about reality. At the quantum level, particles don't have definite positions or velocities until they're measured. Instead, they exist in what physicists call a superposition, a state where all possible positions or velocities exist simultaneously, each with a certain probability. This isn't because we lack information. It's a fundamental feature of reality at small scales. Imagine an electron in an atom. Before you measure its position, it doesn't occupy a specific point in space. Instead, it exists as a cloud of probability, more likely to be found in some regions than others. This probability cloud is described by something called a wave function, which evolves according to mathematical equations that tell us how the probabilities change over time. The act of measurement is where things get truly weird. When you actually detect the electron's position, the wave function collapses, and the electron suddenly has a definite location. Before measurement, it was everywhere in the cloud simultaneously. After measurement, it's in one place. This isn't a limitation of our measuring devices. It appears to be how nature fundamentally works. One of the most mind-bending aspects of quantum mechanics is wave-particle duality. Light, which we often think of as a wave, also behaves like particles called photons. Electrons, which we think of as particles, can also behave like waves. In fact, everything in the universe has both wave and particle properties. The famous double-slit experiment demonstrates this beautifully. If you shine light through two narrow slits onto a screen, you see an interference pattern, alternating bright and dark bands, just like waves on water would create. This proves light is a wave. But if you make the light very dim, so that only one photon passes through at a time, something remarkable happens. Each photon hits the screen at a single point, like a particle. Yet, if you wait long enough, the individual impacts build up the same interference pattern, meaning each photon somehow knows about both slits, as if it traveled through both simultaneously. This duality extends to matter. Electrons can create interference patterns just like light waves. In fact, the structure of atoms depends on this wave nature. Electrons in atoms can only occupy certain energy levels, not because there's anything physically preventing them from existing at other energies, but because only certain wavelengths fit properly around the nucleus. Think of it like the standing waves on a guitar string. Only certain frequencies resonate properly. Another cornerstone of quantum mechanics is Heisenberg's uncertainty principle. This states that certain pairs of properties like position and momentum cannot both be known precisely at the same time. The more accurately you know a particle's position, the less accurately you can know its momentum, and vice versa. This isn't about measurement errors. It's a fundamental limit built into the nature of reality. The uncertainty principle arises from the wave nature of matter. A wave that's spread out in space has a well-defined wavelength, which relates to momentum. But a wave that's spread out doesn't have a precise location. To confine a wave to a small region, you need to combine many different wavelengths, which means the momentum becomes uncertain. You can't have it both ways. Precision in position requires uncertainty in momentum. This principle has profound implications. It means that even in empty space, in what we call a vacuum, there's constant activity. Quantum fields fluctuate, and pairs of particles and antiparticles briefly pop into existence before annihilating each other again. These quantum fluctuations are real and have measurable effects. They influence the behavior of atoms, and can even, as we'll see later, play a role in the large-scale structure of the universe. Everything that happens in the universe, from the smallest atomic interaction to the formation of galaxies, is governed by four fundamental forces. We've already discussed gravity in detail. The other three are electromagnetism, the strong nuclear force, and the weak nuclear force. Electromagnetism is the force between electrically charged particles. It's responsible for chemistry, electricity, magnetism, and light itself. When electrons in atoms shift between energy levels, they emit or absorb photons, particles of light. The entire spectrum of electromagnetic radiation, from radio waves to gamma rays, is part of this single force. It's electromagnetic forces that hold molecules together, that make your hand unable to pass through a table, and that transmit signals in your nervous system. The strong nuclear force is what holds atomic nuclei together. Protons, all positively charged, would normally repel each other electrically, but the strong force overwhelms this repulsion at very short distances, binding protons and neutrons into stable nuclei. This force is incredibly powerful, about 100 times stronger than electromagnetism at nuclear distances. But it has a very short range, only about 10 to the negative 15 meters, the size of a nucleus. The weak nuclear force is responsible for certain types of radioactive decay and plays a crucial role in the nuclear reactions that power stars. Despite being weak, it's strong enough to change one type of quark into another, converting protons into neutrons or vice versa. This is essential for stellar fusion, where hydrogen nuclei combine to form helium. In the quantum picture, forces are actually carried by particles. Photons carry the electromagnetic force, gluons carry the strong force, and W and Z bosons carry the weak force. Gravity, in this framework, would be carried by hypothetical particles called gravitons, though we haven't detected them yet. The modern understanding of particle physics is based on quantum field theory, which combines quantum mechanics with special relativity. In this view, space is filled with fields for each type of particle: an electron field, a photon field, a quark field, and so on. What we call particles are actually excitations or vibrations in these fields, like waves on the surface of an ocean. When particles interact, they exchange quanta of other fields. When two electrons repel each other, they're exchanging photons of the electromagnetic field. These exchange photons are called virtual particles because they exist only during the interaction, popping into existence and vanishing in accordance with the uncertainty principle. The standard model of particle physics is our most successful description of the quantum world. It categorizes all known fundamental particles and describes how they interact through 3 of the 4 forces. Gravity isn't included because we don't yet have a quantum theory of gravity that's compatible with the standard model. Despite its success, we know the standard model is incomplete. It doesn't explain dark matter or dark energy, which we'll discuss later, and it doesn't include gravity. Finding a more complete theory is one of the great challenges of modern physics. After recombination, when the universe became transparent, there was a long period that astronomers call the cosmic dark ages. The universe was filled with hydrogen and helium gas, but there were no stars yet to light it up. However, the gas wasn't perfectly uniform. Quantum fluctuations from the inflationary era had left tiny variations in density, with some regions slightly more dense than others. Gravity amplified these small differences. Denser regions attracted more matter, becoming even denser, while less dense regions lost matter and became emptier. This process, called gravitational collapse, led to the formation of the first stars probably around 200 million years after the Big Bang. These first-generation stars, called population 3 stars, were very different from modern stars. They contained almost no elements heavier than helium because those elements hadn't been created yet. Population 3 stars were enormous, some perhaps 100 or even several hundred times the Sun's mass. They burned hot and fast, living only a few million years before exploding as supernovae. But in their brief lives they accomplished something crucial. They created the first heavy elements. Let me explain how stars generate energy and why they're so important to the story of the universe. A star forms when a cloud of gas collapses under its own gravity. As the cloud contracts, gravitational potential energy converts to heat, warming the center. When the core temperature reaches about 10 million degrees Kelvin, nuclear fusion begins. Fusion is the process where lighter atomic nuclei combine to form heavier nuclei, releasing energy in the process. In the Sun and similar stars, the primary reaction is the fusion of hydrogen into helium. 4 hydrogen nuclei combine through a series of steps to create 1 helium nucleus. If you carefully account for the masses, you find that the helium nucleus weighs slightly less than the 4 hydrogen nuclei you started with. That missing mass has been converted to energy according to Einstein's relationship. Energy equals mass times the speed of light squared. The amount of energy released is staggering. Every second, the Sun converts approximately 600 million tons of hydrogen into helium, and about 4 million tons of matter is converted to pure energy. This energy works its way from the core to the surface and then radiates into space as light and heat. The energy released creates an outward pressure that balances gravity's inward pull, stabilizing the star. This balance between gravity and pressure determines how a star lives and how it dies. More massive stars have stronger gravity, requiring higher core temperatures and pressures to maintain balance. These higher temperatures mean more rapid fusion, so massive stars burn through their fuel much faster than smaller stars. A star 10 times the Sun's mass might live only 20 million years, while the Sun will shine for about 10 billion years, and the smallest stars might last for trillions of years. Here's one of the most profound realizations in all of science. With the exception of hydrogen, helium, and traces of lithium made in the Big Bang, every atom in your body, every atom in Earth, was created inside stars or in stellar explosions. Carl Sagan famously said, "We are made of star stuff," and this is literally true. When a star exhausts the hydrogen in its core, it begins to contract, heating up until it's hot enough to fuse helium into carbon and oxygen. In massive stars, this process continues through multiple stages, creating neon, magnesium, silicon, and eventually iron. Each fusion stage produces heavier elements and releases energy, though each successive stage yields less energy than the one before. Iron is the end of the line for fusion as an energy source. Fusing iron nuclei into heavier elements requires energy rather than releasing it, so once a massive star's core turns to iron, fusion stops. With no energy source to counteract gravity, the core collapses catastrophically in less than a second. The outer layers crash inward and then rebound in a tremendous explosion called a supernova. During a supernova, several remarkable things happen simultaneously. The explosion is so violent and energetic that fusion reactions occur that couldn't happen during normal stellar burning, creating elements heavier than iron, including gold, platinum, uranium, and all the other heavy elements in the periodic table. The explosion also blasts all these newly created elements into space, enriching the interstellar medium with heavy elements that can be incorporated into new generations of stars and planets. While the first stars were forming, the large-scale structure of the universe was also taking shape. Those tiny density fluctuations from the early universe were the seeds of galaxies and galaxy clusters. Gravity pulled matter toward the densest regions, creating a cosmic web of structure. Filaments and sheets of galaxies separated by vast empty voids. A galaxy is essentially a gravitationally bound collection of stars, gas, dust, and dark matter, which we'll discuss shortly. Our Milky Way galaxy contains somewhere between 100 billion and 400 billion stars, along with their planets, stellar remnants, and clouds of gas and dust. The visible matter in our galaxy orbits around the center, held together by gravity. Our solar system, located about 26,000 light-years from the galactic center, takes approximately 230 million years to complete one orbit. Galaxies come in various shapes and sizes. Spiral galaxies, like the Milky Way, have rotating disks of stars with elegant spiral arms, along with a central bulge and a spherical halo of older stars. Elliptical galaxies are more rounded or football-shaped, with less organized stellar orbits and typically older stellar populations. Irregular galaxies lack a well-defined structure, often because they've been disrupted by gravitational interactions with other galaxies. Galaxies aren't isolated. They attract each other gravitationally and often collide and merge. When this happens, the individual stars rarely collide because space between stars is so vast, but the galaxy's shapes are dramatically distorted by tidal forces. Gas clouds within colliding galaxies compress, triggering bursts of new star formation. Over billions of years, two galaxies can completely merge into a single, larger galaxy. In fact, the Milky Way is currently absorbing several smaller satellite galaxies, and in about 4 billion years will collide with the Andromeda Galaxy, our nearest large galactic neighbor. One of the most important discoveries in cosmology came in the 1920s, when astronomer Edwin Hubble measured the velocities and distances of galaxies. He found something remarkable. Almost all galaxies are moving away from us, and the farther away they are, the faster they're receding. This relationship, now called Hubble's law, showed that the universe itself is expanding. Imagine the universe as the surface of a balloon being inflated. Dots drawn on the balloon represent galaxies. As the balloon expands, every dot moves away from every other dot, not because the dots are moving through the rubber, but because the rubber itself is stretching. Similarly, galaxies aren't moving through space. Space itself is expanding, carrying galaxies along with it. The expansion rate is characterized by the Hubble constant, which tells us how fast space is expanding. Currently, space expands such that galaxies approximately 70 kilometers per second faster for every megaparsec of distance between them. A megaparsec is about 3.26 million light-years. This means a galaxy 1 megaparsec away recedes at 70 kilometers per second, while a galaxy 2 megaparsecs away recedes at about 140 kilometers per second. If the universe is expanding, then it must have been smaller in the past. Extrapolating backward, we reach the Big Bang, confirming that the universe had a beginning. The expansion also explains one of the oldest cosmological puzzles. Why is the sky dark at night? If the universe were infinite, eternal and static, every line of sight should eventually hit a star, making the entire sky as bright as the sun's surface. The expansion, combined with the universe's finite age, means light from very distant stars hasn't reached us yet, leaving most of the sky dark. In the 1930s, astronomer Fritz Zwicky studied the motions of galaxies in the Coma cluster. He found something puzzling. The galaxies were moving so fast that the cluster's gravity, based on its visible mass, should be far too weak to hold them together. They should have flown apart long ago. He proposed that there must be a large amount of invisible matter, which he called dark matter, providing the extra gravity needed. For decades, this observation was largely ignored or considered an anomaly. But in the 1970s, astronomer Vera Rubin made careful measurements of how stars orbit in spiral galaxies. According to Newton's laws, stars farther from a galaxy's center should orbit more slowly, just as outer planets in our solar system orbit more slowly than inner planets. But Rubin found that stars in the outer regions of galaxies orbit just as fast as those closer to the center. There's only one reasonable explanation. Galaxies are surrounded by enormous halos of invisible matter, far more massive than all the visible stars and gas combined. This dark matter doesn't emit, absorb, or reflect light, making it invisible to telescopes. We can only detect it through its gravitational effects. Despite decades of research, we still don't know what dark matter is made of. We know it's not ordinary matter made of protons, neutrons and electrons, because if it were, it would interact with light, and we'd see it. Current evidence suggests dark matter consists of some exotic particle that interacts only through gravity and possibly the weak nuclear force. Leading candidates include particles called WIMPs, standing for weakly interacting massive particles. These hypothetical particles would have significant mass, perhaps tens or hundreds of times the proton's mass, but would rarely interact with ordinary matter. Billions of WIMPs might be passing through your body every second, but because they interact so weakly, they pass right through without you noticing. Another possibility is axions, much lighter hypothetical particles that were originally proposed to solve problems in particle physics, but could also make up dark matter. Multiple experiments are currently searching for dark matter particles, either by trying to detect rare interactions with ordinary matter or by attempting to create dark matter particles in particle accelerators. Whatever dark matter is, it's crucial to the universe's structure. Computer simulations show that without dark matter, galaxies as we know them couldn't form. Dark matter provides the gravitational scaffolding upon which ordinary matter accumulates, eventually forming stars and galaxies. In a very real sense, we owe our existence to dark matter. even though we still don't fully understand what it is. Based on observations of the cosmic microwave background and the large-scale structure of the universe, we can determine what percentage of the universe's total mass and energy comes from different sources. Ordinary matter, everything made of atoms, comprises only about 5% of the universe's total content. Dark matter makes up about 27%. But this still leaves most of the universe unaccounted for. In the late 1990s, two teams of astronomers were using distant supernova to measure the expansion history of the universe. They expected to find that the expansion was slowing down due to gravity, which pulls everything together. Instead, they discovered something shocking. The expansion is speeding up. This acceleration requires some form of energy that creates a repulsive gravitational effect, pushing space apart. Physicists call it dark energy, though the name tells us nothing about what it actually is. Dark energy makes up about 68% of the universe's total content, making it the dominant component. The simplest explanation for dark energy is that it's the energy of empty space itself, what physicists call vacuum energy, or the cosmological constant. According to quantum field theory, even empty space isn't truly empty, but filled with quantum fields undergoing fluctuations. These fluctuations have energy, and Einstein's general relativity tells us that energy curves spacetime, which we experience as gravity. Here's the truly bizarre part. Vacuum energy creates a repulsive gravitational effect. While ordinary matter and even dark matter attract each other gravitationally, vacuum energy pushes space apart. As the universe expands and matter becomes more dilute, the average density of ordinary and dark matter decreases. But vacuum energy, if that's what dark energy is, has the same density everywhere and always. As the universe expands, there's more space, and thus more vacuum energy, making the repulsive effect stronger over time. There's a deep mystery here. When physicists try to calculate how much vacuum energy there should be based on quantum field theory, they get an absurdly large number, bigger than what we observe by a factor of about 10 to the 120 power. This is called the cosmological constant problem, and it's one of the biggest unsolved problems in theoretical physics. If vacuum energy were as large as quantum theory suggests, the universe would have expanded so rapidly that galaxies, stars and planets could never have formed. Clearly, something we don't understand is going on. Maybe there's some mechanism that cancels out most of the vacuum energy, or perhaps dark energy isn't vacuum energy at all, but something else entirely. Another possibility is that dark energy isn't constant, but changes over time. If this is true, dark energy would be a dynamic field, sometimes called quintessence, that evolves as the universe expands. Researchers are trying to determine whether dark energy's density changes by making precise measurements of the expansion rate at different times in cosmic history. The existence of dark energy has profound implications for the universe's ultimate fate, which we'll explore shortly. But first, let's understand how all these components, ordinary matter, dark matter and dark energy, fit together to create the universe we observe. We mentioned earlier that quantum fluctuations in the early universe created tiny variations in density. These fluctuations were incredibly small, only about 1 part in 100,000 difference between the densest and least dense regions. Yet over billions of years, gravity amplified these minute differences into the magnificent cosmic web of structure we see today. Let me walk you through how this happens. Imagine a region that's slightly denser than average. Its extra gravity attracts nearby matter, pulling it in and making the region even denser. Meanwhile, less dense regions lose matter to their denser neighbours, becoming even more empty. This process is self-reinforcing. Denser regions become denser and voids become emptier. But there's a complication. The expanding universe works against gravitational collapse. Space is stretching, pulling matter apart, while gravity is trying to pull it together. Which force wins depends on the scale and the time period. On small scales, gravity wins fairly quickly, allowing structures to collapse. On very large scales, expansion dominates, preventing collapse. There's a complex interplay between expansion and gravitational collapse that determines how structure forms. Dark matter plays the starring role in structure formation because it makes up most of the mass and because it doesn't interact with radiation. After the Big Bang, ordinary matter was initially too hot and coupled to radiation to collapse efficiently. But dark matter, unaffected by radiation, could begin collapsing earlier, creating gravitational wells into which ordinary matter later fell. If you could see the distribution of galaxies on the largest scales, the universe would resemble a vast three-dimensional spider web. Long filaments of galaxies stretch across hundreds of millions of light-years, connecting at dense nodes where galaxy clusters form. Between these filaments lie enormous voids, vast regions containing very few galaxies, each tens or hundreds of millions of light-years across. This cosmic web is a direct reflection of those initial quantum fluctuations, stretched and amplified by billions of years of gravitational evolution. Computer simulations that start with just the simple initial conditions from the early universe and then let gravity and expansion operate according to known physics produce cosmic web patterns remarkably similar to what we observe. Galaxy clusters, the nodes where filaments intersect, are the largest gravitationally bound structures in the universe. A large cluster might contain thousands of galaxies and have a total mass of over 1 quadrillion, 10 to the 15, solar masses. Most of this mass is dark matter, with ordinary matter split between the galaxies and hot gas that fills the space between them. This intergalactic gas is so hot, tens of millions of degrees, that it emits X-rays, allowing us to map it with X-ray telescopes. Nearly every large galaxy has a supermassive black hole at its center. The Milky Way's central black hole has a mass of about 4 million times the Sun's mass, while some galaxies host black holes billions of times more massive than the Sun. These giants play a surprisingly important role in galaxy evolution. When matter falls toward a supermassive black hole, it doesn't plunge straight in. Instead, it forms a rotating disk called an accretion disk. Friction in the disk heats the matter to millions of degrees, causing it to radiate enormous amounts of energy, often outshining all the stars in the galaxy combined. These actively feeding black holes, called active galactic nuclei or quasars, can be seen across billions of light-years of space. The energy released by active galactic nuclei can blow away the galaxy's gas, shutting down star formation. This feedback mechanism appears to regulate galaxy growth, preventing galaxies from becoming much larger than we observe. There's a remarkable relationship between a galaxy's total mass and the mass of its central black hole, suggesting they've evolved together in a carefully balanced dance. One of the most powerful tools for studying dark matter is gravitational lensing. Remember that mass curves spacetime, and light follows the curvature of spacetime. When light from a distant galaxy passes near a massive object like a galaxy cluster, the cluster's gravity bends the light's path, acting like a lens. Sometimes this creates multiple images of the background galaxy, or stretches it into arcs and rings around the lensing cluster. By carefully measuring these distortions, astronomers can map the distribution of mass in the cluster, including dark matter. These maps show that dark matter is distributed in vast halos surrounding and extending far beyond the visible galaxies. In some cases, gravitational lensing has revealed remarkable phenomena. There are clusters where the dark matter appears to be separated from the ordinary matter, likely due to collisions between clusters. When two clusters collide, their dark matter halos pass through each other mostly unaffected, because dark matter doesn't interact electromagnetically. But the hot gas, which is ordinary matter, slams into the other cluster's gas and slows down. This separation of dark matter from ordinary matter provides powerful evidence that dark matter really exists and isn't just an error in our understanding of gravity. Every star is born, lives a life whose length and character depend on its mass, and eventually dies. Let's trace this cycle in more detail, as it's central to understanding how the universe creates complexity from simplicity. Low-mass stars, like red dwarfs, less than half the Sun's mass, burn their hydrogen so slowly that none have reached the end of their lives yet. The universe simply isn't old enough. These thrifty stars will shine for trillions of years, long after stars like the Sun have burned out. The Sun is a medium-mass star, currently about 4.6 billion years old and roughly halfway through its main life stage. For another 5 billion years, it will continue fusing hydrogen into helium in its core. But eventually the hydrogen will run out. When that happens, the core will contract and heat up, while the outer layers expand dramatically. The Sun will become a red giant, swelling to perhaps 100 times its current size, possibly engulfing Earth. In the red giant phase, the core becomes hot enough to fuse helium into carbon and oxygen. This stage is shorter than the hydrogen-burning phase, lasting perhaps 1 billion years. The Sun doesn't have enough mass to progress beyond carbon and oxygen fusion, so once the helium is exhausted, the core will contract one final time, while the outer layers puff off into space, creating a beautiful planetary nebula. The core becomes a white dwarf, a star about Earth's size but with half the Sun's mass, incredibly dense, supported not by fusion but by quantum mechanical pressure from electrons packed tightly together. Massive stars, those more than about 8 times the Sun's mass, live fast and die spectacularly. Their higher gravity requires higher core temperatures and pressures, leading to rapid fusion. A star 20 times the Sun's mass might live only 10 million years, 1,000 times shorter than the Sun's lifespan. But massive stars can fuse elements beyond helium. After exhausting hydrogen, they fuse helium into carbon and oxygen, then carbon into neon and magnesium, then neon into oxygen and magnesium, then oxygen into silicon and sulfur. Finally, silicon into iron and nickel. Each stage is shorter than the last because each releases less energy per kilogram of fuel. The silicon burning stage might last only a few days. The star develops an onion-like structure with layers of different elements. Iron in the core, surrounded by shells of silicon, oxygen, carbon, helium, and finally hydrogen at the surface. Iron is the end point because fusing iron into heavier elements requires energy rather than releasing it. Once the core is iron, the star's days are numbered. When the iron core reaches about 1.4 solar masses, it can no longer support itself. Electrons are forced to combine with protons, forming neutrons and releasing neutrinos. In less than a second, the core collapses from about the size of Earth to a ball perhaps 20 kilometers across. The collapse is so rapid that it rebounds, sending a shockwave outward through the star's layers. This shockwave, powered partly by the neutrinos streaming from the collapsed core, blasts the star's outer layers into space at speeds of 10,000 kilometers per second or more. For a few weeks, the supernova can outshine its entire host galaxy. In that brief time, it releases more energy than the Sun will emit in its entire 10 billion-year lifetime. The supernova explosion creates heavy elements through rapid nuclear reactions in the intense heat and pressure. Elements heavier than iron, including gold, platinum and uranium, are forged primarily in supernova. When you wear gold jewelry, you're wearing atoms that were created in the death throes of a massive star billions of years ago. The collapsed core left behind after a supernova can become one of 2 exotic objects, depending on its mass. If the core is between about 1.4 and 3 solar masses, it becomes a neutron star. This is matter compressed to incredible density, about the same as an atomic nucleus. A neutron star with 1.4 times the Sun's mass would be only about 20 kilometers in diameter. A teaspoon of neutron star material would weigh about 1 billion tons on Earth. Neutron stars are supported against further collapse by neutron degeneracy pressure, a quantum mechanical effect. When neutrons are packed so tightly that they're essentially touching, the uncertainty principle prevents them from being squeezed closer together. It's similar to the electron degeneracy that supports white dwarfs, but much stronger. Many neutron stars are pulsars, emitting beams of radio waves from their magnetic poles. As the star rotates, these beams sweep across space like lighthouse beams. If Earth lies in the path of a beam, we detect regular pulses of radio emission, sometimes hundreds of times per second. These rotating neutron stars have incredibly strong magnetic fields, trillions of times stronger than Earth's, and they keep time more accurately than atomic clocks. If the stellar core exceeds about 3 solar masses, nothing can stop its collapse. Not electron degeneracy pressure, not neutron degeneracy pressure, not any known force in physics. The core collapses into a black hole, a region where space-time curvature becomes so extreme that even light cannot escape. At the center of a black hole, general relativity predicts a singularity, a point where density becomes infinite and the known laws of physics break down. We don't know what happens at a singularity because our theories can't handle such extreme conditions. This suggests we need a quantum theory of gravity to fully understand black holes. Around the singularity lies the event horizon, the point of no return. Its radius, called the Schwarzschild radius, depends only on the black hole's mass. For a black hole with the Sun's mass, the event horizon would be about 3 kilometers in radius. For a supermassive black hole of 1 billion solar masses, it would be about 3 billion kilometers, roughly 20 times the Earth-Sun distance. Black holes aren't cosmic vacuum cleaners as often portrayed. If the Sun suddenly became a black hole, which it can't, as it lacks the mass, Earth's orbit wouldn't change. The gravitational pull at Earth's distance would be exactly the same. You only notice strange effects when you get very close to the event horizon. For centuries, humans wondered whether other stars had planets, but we had no way to find out. Planets don't produce their own light, and they're tiny compared to stars, making them incredibly difficult to detect across interstellar distances. Then, in 1995, astronomers detected the first planet orbiting a Sun-like star, and the floodgates opened. Today, we know of over 5,000 exoplanets, with more discovered regularly. Most exoplanets are detected indirectly. The most successful method is the transit technique. If a planet's orbit is aligned just right from our viewpoint, the planet will pass in front of its star once per orbit, blocking a tiny fraction of the star's light. By measuring this periodic dimming, we can detect the planet and determine its size and orbital period. NASA's Kepler mission, using this technique, discovered thousands of planets. Another method measures the star's wobble. A planet doesn't actually orbit the star. Rather, both planet and star orbit their common center of mass. For a large planet or one close to its star, this wobble is detectable by measuring Doppler shifts in the star's spectrum. As the star moves toward us, its light is slightly blue shifted. As it moves away, it's slightly red shifted. From these measurements, we can determine the planet's mass and orbit. The exoplanets we've discovered have revolutionized our understanding of planetary systems. Before these discoveries, our only example was our solar system, and we assumed it was typical. We now know planetary systems come in remarkable variety. Many systems have hot Jupiters, gas giant planets orbiting extremely close to their stars, completing orbits in just a few days. These planets likely formed farther out and then migrated inward, either through interactions with the protoplanetary disk or through gravitational interactions with other planets. This migration process can disrupt entire planetary systems, sometimes ejecting planets into interstellar space. We've found systems with planets in orbits that would be unstable over millions of years, suggesting they're young or in transitional states. We've found planets orbiting binary star systems experiencing the gravitational pull of two suns. We've found free-floating planets drifting through the galaxy, untethered to any star. The diversity suggests planet formation is common, but can proceed along many different pathways. From an astrobiological perspective, the most interesting planets are those in their star's habitable zone, the region where temperatures permit liquid water on a planet's surface. Water is essential for all life as we know it, serving as a solvent for biochemistry and having unique properties that make it ideal for life's chemical reactions. The habitable zone's location depends on the star's temperature and luminosity. For the Sun, it extends roughly from Venus's orbit to just beyond Mars. For cooler red dwarf stars, which are much dimmer, the habitable zone is much closer to the star. For hotter, more luminous stars, it's farther out. But being in the habitable zone doesn't guarantee a planet is habitable. Venus is arguably in the Sun's habitable zone, but its thick carbon dioxide atmosphere creates a runaway greenhouse effect, heating the surface to 460 degrees Celsius, hot enough to melt lead. Mars is near the outer edge of the habitable zone, but its thin atmosphere and lack of a magnetic field have allowed solar wind to strip away most of its atmosphere, leaving it cold and dry. What makes a planet truly habitable? We're still learning, but several factors seem important. The planet needs to be large enough to retain an atmosphere through its gravity, but not so large that it accumulates a thick hydrogen atmosphere like a gas giant. Earth's size appears to be in a sweet spot. A magnetic field helps protect the atmosphere from stellar wind. Earth's magnetic field is generated by its liquid iron core, which convects and acts like a dynamo. Mars likely had a magnetic field billions of years ago, but lost it when its core cooled and solidified, after which its atmosphere was gradually stripped away. Plate tectonics might be important for long-term habitability. Earth's shifting plates recycle carbon between the atmosphere, oceans and rocks, regulating atmospheric carbon dioxide and thus temperature over geological timescales. Without this carbon cycle, Earth might have frozen over or developed a Venus-like greenhouse atmosphere long ago. The presence of a large moon like Earth's might help stabilize a planet's axial tilt, preventing extreme climate variations. The chemical composition matters too. A planet needs the right elements to support complex chemistry, including carbon, hydrogen, nitrogen, oxygen, phosphorus and sulfur, the building blocks of life as we know it. How common is life in the universe? The Drake equation proposed by astronomer Frank Drake breaks this question into factors we can estimate. The rate of star formation, the fraction of stars with planets, the number of habitable planets per star, the fraction where life develops, the fraction where life becomes intelligent, and so on. With our current knowledge, Estimates for the number of technological civilizations in the galaxy range from one, us, to potentially millions, depending on which values you assume for the uncertain factors. The fact that we haven't detected any signs of extraterrestrial technology despite decades of searching is called the Fermi paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" Possible explanations range from the optimistic, civilizations are common but communicate in ways we haven't thought to look for, to the sobering, intelligent life is extremely rare or tends to destroy itself shortly after developing technology, to the unsettling, advanced civilizations deliberately avoid contact. The truth could be something we haven't even considered. What we can say is that the ingredients for life seem to be common. Organic molecules, the complex carbon-based compounds essential for life, have been detected in interstellar clouds, on asteroids, and in the atmosphere of Saturn's moon Titan. The chemical building blocks are out there. Whether they assemble into living systems, and how often, remains one of the great unanswered questions. Let's project forward and consider the universe's future. Over the next several trillion years, star formation will gradually decline as galaxies exhaust their supplies of hydrogen gas. The universe will grow darker as fewer and fewer new stars ignite. Eventually, perhaps 100 trillion years from now, the last star will form. Existing stars will continue to shine for varying lengths of time, depending on their mass. The smallest red dwarfs will burn for tens of trillions of years. As each star exhausts its fuel, it will die, leaving behind white dwarfs, neutron stars, or black holes. The universe will increasingly be populated by stellar remnants rather than actively shining stars. White dwarfs, no longer generating energy, will gradually cool and fade, eventually becoming black dwarfs, cold, dark spheres, invisible against the darkness of space. This cooling takes an incredibly long time, likely longer than the current age of the universe, so no black dwarfs exist yet. Over even longer timescales, gravitational interactions will disrupt stellar systems. Stars will occasionally pass close to each other, exchanging energy. Some stars will be flung out of their galaxies into intergalactic space. Others will spiral inward toward the central supermassive black hole and eventually be consumed. After perhaps 10 to the 20th years, 100 quintillion years, galaxies may dissolve, with most stars ejected into the void and the remainder swallowed by black holes. After all stars have died and galaxies have evaporated, the universe will enter an era dominated by black holes. But even black holes aren't eternal. In 1974, Stephen Hawking showed that black holes slowly evaporate through a quantum mechanical process now called Hawking radiation. Here's how it works. Remember the quantum fluctuations we discussed, where particle-antiparticle pairs briefly pop into existence in empty space? Near a black hole's event horizon, one particle of a pair might fall into the black hole, while the other escapes. To an outside observer, it appears the black hole emitted a particle. Over time, this process causes the black hole to lose mass. For stellar mass and supermassive black holes, Hawking radiation is incredibly weak, much colder than the cosmic microwave background, so black holes are actually absorbing more energy than they emit. But as the universe expands and the background radiation cools, eventually the radiation will become cooler than the black holes, and they'll begin to evaporate. A solar mass black hole would take about 10 to the 67 years to evaporate completely. A supermassive black hole of 1 billion solar masses would require about 10 to the 100 years. These timescales are so vast they're almost meaningless, millions of times longer than the current age of the universe. If dark energy remains constant, the universe's expansion will continue accelerating forever. Galaxies outside our local group, which are gravitationally bound together, will accelerate away from us ever faster. Eventually, they'll recede faster than light can travel through space, disappearing beyond our cosmic horizon, forever beyond our ability to see or reach. After all black holes have evaporated, the universe will reach a state sometimes called heat death, maximum entropy, with all usable energy exhausted. All matter will have decayed into elementary particles spread thinly through an ever-expanding void. The temperature will approach absolute zero. Nothing interesting can happen anymore because there's no energy available to make things happen. But even this may not be the end. Some theories suggest protons themselves might be unstable, decaying into lighter particles over timescales of perhaps 10 to the 40 years or longer. If so, all matter will eventually dissolve. Other theories propose that the vacuum itself might be unstable, and the universe could undergo a phase transition into a lower energy vacuum state, possibly with different physical laws. The universe's ultimate fate depends critically on the nature of dark energy. If dark energy is truly constant, the accelerating expansion continues forever. But if dark energy weakens over time, the universe might eventually stop accelerating and even start contracting, leading to a big crunch where everything collapses back into a hot, dense state, possibly followed by another Big Bang. Another possibility is the Big Rip. If dark energy not only exists but grows stronger over time, the accelerating expansion could become so extreme that it eventually tears apart galaxies, stars, planets, and even atoms and subatomic particles. This scenario would end not with a whimper, but with a violent destruction of all structure. Currently, observations suggest dark energy is consistent with being constant, pointing toward the heat death scenario. But our measurements aren't precise enough to rule out other possibilities. Future observations of distant supernovae and the cosmic microwave background will help us determine dark energy's properties more accurately. As we contemplate the universe's workings and its ultimate fate, we can't help but notice something remarkable. The fundamental constants of physics appear to be fine-tuned for the existence of complex structures like stars, planets, and life. If gravity were slightly stronger, stars would burn too quickly for life to evolve. If it were weaker, stars might never form. If the strong nuclear force were slightly different, stable atoms wouldn't exist. This apparent fine-tuning has led to much speculation. The anthropic principle suggests that we observe these particular values because if they were different, we wouldn't exist to observe them. It's a selection effect. we can only exist in a universe capable of supporting our existence. Some scientists propose the multiverse hypothesis. Perhaps there are countless universes, each with different physical constants, and we happen to inhabit one where the constants permit our existence. Most universes would be sterile, incapable of supporting life or even complex structures, but we obviously wouldn't find ourselves in those. Others argue that invoking universes we can never observe or test is outside the realm of science. Perhaps there's a deeper theory we haven't discovered yet that explains why the constants have the values they do. Or perhaps the apparent fine-tuning is an illusion, and life could arise under a wider range of conditions than we currently imagine. One of the great goals of theoretical physics is to unify all four fundamental forces into a single theoretical framework. We've made significant progress. The electromagnetic and weak nuclear forces were unified in the 1960s into the electroweak force, a single force that appears as two distinct forces at low energies, but reveals its unified nature at high energies. The strong nuclear force has been incorporated with the electroweak force into the standard model of particle physics, though this is more a combination than a true unification. The standard model successfully describes all known particle interactions except gravity with remarkable precision. Gravity remains the holdout. General relativity describes gravity beautifully at large scales, but it's a classical theory, incompatible with quantum mechanics. When we try to apply quantum mechanics to gravity, we get nonsensical infinities in our calculations. This suggests we need a quantum theory of gravity. String theory is perhaps the most developed attempt at quantum gravity. It proposes that the fundamental constituents of reality aren't point-like particles, but tiny one-dimensional strings, perhaps 10 to the negative 35 meters long. Different vibration patterns of these strings correspond to different particles. One pattern is an electron, another a quark, another a photon, and so on. String theory requires extra spatial dimensions beyond the three we experience. The most studied version requires 10 total dimensions, 9 space, 1 time. Where are these extra dimensions? The theory suggests they're curled up so small we can't detect them, like how a garden hose looks one-dimensional from far away, but has a circular cross-section when you look closely. String theory makes predictions that differ from other theories only at incredibly high energies or small scales, far beyond our current experimental capabilities. This makes it difficult to test, leading some physicists to question whether it's science or mathematics. Supporters argue that string theory's mathematical consistency and its ability to include gravity quantum mechanically make it a promising avenue to explore. An alternative approach to quantum gravity is loop quantum gravity. Unlike string theory, which tries to unify all forces, loop quantum gravity focuses specifically on making gravity quantum mechanical while leaving other forces as they are in the standard model. Loop quantum gravity suggests that space itself is quantized, made of discrete units rather than being infinitely divisible. Space would have a grainy structure at the Planck scale, about 10 to the negative 35 meters, like how matter is made of atoms rather than being continuous. This quantization of space might resolve the singularities that plague our understanding of black holes and the Big Bang. Both string theory and loop quantum gravity make predictions about what happens inside black holes and at the moment of the Big Bang that differ from classical general relativity. Unfortunately, these predictions are difficult to test with current technology. This remains an active area of research, with physicists searching for observable consequences of these theories. Despite quantum mechanics' incredible success in predicting experimental results, deep conceptual mysteries remain. The measurement problem asks, why does the act of measurement cause the wave function to collapse? Before measurement, a particle exists in a superposition of states. After measurement, it has a definite state. What exactly counts as a measurement, and why does it have this special role? The Copenhagen interpretation, the standard view taught in textbooks, simply accepts measurement as a fundamental process without trying to explain it. But this is philosophically unsatisfying. How can measurement be fundamental when measurements are performed by measurement devices, which are themselves made of quantum particles? The many worlds interpretation offers a radical alternative. The wave function never collapses. Instead, when a measurement is made, the universe splits into multiple branches, one for each possible outcome. In one branch, you measure the particle spin up. In another branch, you measure its spin down. Both outcomes happen. You just experience only one branch. This avoids the measurement problem, but at the cost of accepting the existence of countless parallel universes. Other interpretations include pilot wave theory, where particles do have definite positions but are guided by a non-local wave, and objective collapse theories, which modify quantum mechanics to include spontaneous collapse of wave functions under certain conditions. The debate continues more than a century after quantum mechanics was developed. Returning to dark matter and dark energy, these remain among the most pressing mysteries in cosmology. Despite decades of effort, we've yet to directly detect a dark matter particle or determine what dark energy is. Some physicists wonder if we're on the wrong track entirely. Perhaps dark matter and dark energy don't exist, and instead our theories of gravity need modification. Several modified Newtonian dynamics, Mound theories, have been proposed that change how gravity works at large scales, attempting to explain galactic rotation curves without invoking dark matter. However, Mound theories struggle to explain all observations, particularly gravitational lensing and the cosmic microwave background. Most physicists still favor dark matter as the best explanation, but remain open to alternatives if evidence emerges. For dark energy, the situation is even more uncertain. Is it truly the cosmological constant, vacuum energy that remains constant throughout space and time? Or is it a dynamic field that evolves? Could it be a sign that general relativity breaks down at cosmological scales? Answering these questions is one of the main goals of modern observational cosmology. Black holes present another puzzle called the information paradox. According to quantum mechanics, information cannot be destroyed. If you know the complete quantum state of a system now, The laws of physics should allow you to determine its state at any past or future time. But what happens to information that falls into a black hole? Hawking radiation suggests black holes eventually evaporate completely. But Hawking radiation, in its original formulation, is thermal and random, carrying no information about what fell into the black hole. If the black hole disappears, taking information with it, this violates quantum mechanics' fundamental principle that information is conserved. Recent work suggests the information might be encoded in subtle correlations in the Hawking radiation so that information is preserved but in a highly scrambled form. This resolution involves deep connections between quantum mechanics, gravity and thermodynamics, and has led to new insights about the nature of spacetime itself. Why does time flow in only one direction? This might seem like a silly question. Time obviously flows from past to future, but fundamental physics laws are time-symmetric. If you recorded any physical process at the microscopic level and played it backward, it would still obey the same laws. Yet, macroscopically, we experience a definite arrow of time. Eggs break, but don't spontaneously reassemble. Living things age and eventually die. And we remember the past, but not the future. The answer lies in entropy, a measure of disorder or randomness. The second law of thermodynamics states that entropy always increases in closed systems. An intact egg has low entropy, high order, while a broken egg has higher entropy, more disorder. We observe time flowing in the direction of increasing entropy. But this just pushes the question back. Why was the entropy so low in the early universe? The Big Bang started with remarkably low entropy, creating a vast reservoir of order that the universe has been spending down ever since. Why the universe began in such a special low-entropy state remains a mystery. Perhaps future theories of quantum gravity will provide an answer. Our understanding of the universe depends on our ability to observe it. An observation means detecting electromagnetic radiation. Visible light, what our eyes can see, is just a tiny slice of the electromagnetic spectrum. To fully understand the cosmos, we observe at all wavelengths, from radio waves millions of times longer than visible light, to gamma rays billions of times more energetic. Each wavelength reveals different aspects of the universe. Radio waves show us cold gas clouds where stars form, and the synchrotron emission from electrons spiraling in magnetic fields. Infrared light penetrates dust that blocks visible light, revealing star formation regions and distant galaxies. Visible light shows us stars and galaxies much as we'd see them with our eyes. Ultraviolet light traces hot, young stars. X-rays reveal hot gas in galaxy clusters and emissions from materials spiraling into black holes. Gamma rays come from the most energetic processes in the universe, including supernovae and jets from supermassive black holes. Earth's atmosphere blocks most of these wavelengths, which is fortunate for life, but inconvenient for astronomy. Water vapor absorbs infrared light. The upper atmosphere absorbs ultraviolet light, protecting us from harmful radiation. X-rays and gamma rays are absorbed high in the atmosphere. This is why we've launched telescopes into space to observe wavelengths that can't penetrate our atmosphere. The Hubble Space Telescope, launched in 1990, revolutionized astronomy by providing unprecedented clear views in visible, ultraviolet and near-infrared light from above the atmosphere's blurring effects. Hubble has observed galaxies from when the universe was less than 1 billion years old, measured the expansion rate of the universe, found evidence for dark energy, and taken iconic images that have brought the beauty of the cosmos to millions of people. The James Webb Space Telescope, launched in 2021, observes primarily in infrared, allowing it to see even farther back in time and peer through dust clouds. Its images have revealed galaxies from when the universe was only a few 100 million years old, shown exoplanet atmospheres in unprecedented detail, and provided insights into star and planet formation. Other space observatories include Chandra, observing X-rays from hot gas and black holes, Spitzer, which observed infrared light before its mission ended, and Fermi, detecting gamma rays from extreme cosmic phenomena. On the ground, giant optical telescopes like the Keck Observatory in Hawaii and the Very Large Telescope in Chile use adaptive optics to compensate for atmospheric blurring, achieving resolution nearly as good as space telescopes. Radio astronomy has its own suite of magnificent instruments. The Very Large Array in New Mexico combines signals from 27 radio dishes to create images with resolution comparable to optical telescopes. The Atacama Large Millimeter Array in Chile observes at short radio wavelengths, revealing coal dust and gas in star-forming regions and distant galaxies. The Event Horizon Telescope, a globe-spanning network of radio dishes working together, created the first image of a black hole shadow in 2019. The detection of gravitational waves opened an entirely new window on the universe. Unlike electromagnetic radiation, which involves photons, gravitational waves are ripples in space-time itself. When massive objects like black holes or neutron stars spiral together and merge, they create gravitational waves that travel outward at the speed of light, alternately stretching and squeezing space as they pass. LIGO, the Laser Interferometer Gravitational Wave Observatory, made the first direct detection in 2015. LIGO uses laser interferometry to measure distance changes smaller than the width of a proton across its 4-kilometer-long arms. When a gravitational wave passes through, it briefly changes the arm lengths by this tiny amount, and LIGO detects the change. Gravitational wave detections have confirmed that black hole mergers occur and provided measurements of black hole masses and spins. The observation of a neutron star merger in 2017, detected in both gravitational waves and electromagnetic radiation, confirmed that such mergers create heavy elements like gold and platinum, and provided an independent measurement of the universe's expansion rate. Future gravitational wave observatories, including space-based detectors like LISA, Laser Interferometer Space Antenna, will detect lower-frequency gravitational waves from supermassive black hole mergers and other sources, opening yet another observational window on the cosmos. Neutrinos are nearly massless particles that interact only through the weak nuclear force and gravity. They're produced in vast numbers by nuclear reactions in stars, supernovae, and other high-energy processes. Because they interact so weakly, neutrinos travel straight through normal matter, almost as if it weren't there. This makes them incredibly difficult to detect, but also means they carry information from regions opaque to light, like the cores of stars and supernovae. Neutrino observatories like IceCube, built into a cubic kilometre of ice at the South Pole, detect the rare occasions when a neutrino does interact, producing charged particles that emit light as they travel through the ice. These detections reveal neutrinos from the Sun, from supernovae, and from distant active galactic nuclei, providing information we couldn't get any other way. In the future, we might even detect gravitational waves and neutrinos from the same event, combining information from multiple messengers to build a complete picture of cosmic phenomena. This multi-messenger astronomy represents the future of how we'll explore the universe. The cosmic microwave background shows that the early universe had almost exactly the same temperature in all directions. This is puzzling because regions on opposite sides of the sky are so far apart that light couldn't have traveled between them in the time since the Big Bang. They're beyond each other's horizons, causally disconnected. So how did they reach the same temperature? Inflation solves this problem elegantly. Before inflation, all the regions we can see today were close together in causal contact, able to reach thermal equilibrium. Then inflation expanded this small region to encompass everything we can observe and more. The regions are only beyond each other's horizons now because of the rapid expansion. Before inflation, they were in contact. This is one of inflation's great successes, explaining why the cosmic microwave background is so uniform. But it raises other questions. What drove inflation? The leading theory involves a quantum field called the inflaton, but we don't know what this field really is or how it relates to other fields in particle physics. The geometry of space can be curved in different ways. Positive curvature, like the surface of a sphere, means parallel lines eventually converge. Negative curvature, like a saddle shape, means parallel lines diverge. Zero curvature, flatness, means parallel lines remain parallel, just like in ordinary Euclidean geometry we learn in school. Observations indicate the universe is spatially flat, or very nearly so. The cosmic microwave background's patterns tell us that if space is curved, the curvature is extremely small. But this flatness is unstable in standard Big Bang cosmology. Any slight deviation from flatness in the early universe would be amplified as time goes on. For the universe to be as flat as we observe today, it must have been extraordinarily flat in the past, fine-tuned to incredible precision. Inflation solves this too. Just as inflating a balloon makes its surface appear flatter to a small observer, cosmic inflation stretched the universe so much that any initial curvature was diluted to near zero. After inflation, the universe naturally emerges flat, or nearly so, regardless of its initial geometry. Particle physics theories predict that the early universe should have produced magnetic monopoles, isolated north or south magnetic poles, rather than the magnetic dipoles with both north and south poles we observe in nature. These monopoles would be massive, stable particles, and if they were produced in the early universe, they should be common today. Yet we've never observed a magnetic monopole. Where are they? Inflation provides an answer. If monopoles were produced before inflation, the exponential expansion would have diluted them to such low density that finding one in the observable universe would be incredibly unlikely. They exist, perhaps, but are so spread out that we're unlikely to ever encounter one. Matter and antimatter are nearly perfect mirror images of each other. For every type of particle, there's a corresponding antiparticle with the same mass but opposite charge. When matter and antimatter meet, they annihilate, converting entirely into energy. The Big Bang should have created equal amounts of matter and antimatter, which would have mostly annihilated, leaving a universe filled with light, but essentially no matter. Obviously, that's not what happened. The universe is made of matter, with little antimatter to be found. This asymmetry between matter and antimatter is called the baryon asymmetry problem. For every billion matter-antimatter pairs created in the early universe, there was apparently one extra matter particle. After all the annihilation, these leftover matter particles became everything we see: stars, galaxies, planets, and us. We don't fully understand what caused this asymmetry. The standard model of particle physics allows for processes that violate matter-antimatter symmetry, but not strongly enough to explain the observed asymmetry. Most physicists suspect that new physics beyond the standard model, active in the early universe when temperatures were much higher, created the imbalance. Discovering what caused this asymmetry is crucial to understanding why we exist. We've travelled from the first instant of creation through 13.8 billion years of cosmic history, explored the fundamental forces and particles that make up reality, journeyed inside stars and black holes, contemplated dark matter and dark energy, and glimpsed the universe's possible fates. Throughout, we've seen how a few simple rules, playing out over vast expanses of space and time, create a cosmos of breathtaking complexity and beauty. The universe began as nearly pure energy in an unimaginably hot, dense state. As it expanded and cooled, forces separated, particles formed, and the first atoms assembled. Gravity pulled matter together, creating the first stars, which forged heavier elements in their cores and scattered them through space when they died. These elements became part of new stars and planets. Around at least one of those planets, perhaps around many, the chemistry of those elements became intricate enough to create life. Every atom in your body except hydrogen was created in a star or stellar explosion. The calcium in your bones, the iron in your blood, the oxygen you breathe, all were forged in nuclear furnaces billions of years ago. You are literally made of stardust, the remnants of countless stellar life cycles spread through space and reassembled into new forms. Modern physics and astronomy have revealed an astonishing amount about how the universe works. We understand the Big Bang's broad outline, the formation of structures, stellar evolution, the expansion of space, and the fundamental particles and forces. We can calculate what happened in the first second after creation and predict what will happen trillions of years in the future. Yet profound mysteries remain. We don't know what dark matter is or what dark energy is, despite them making up 95% of the universe. We don't understand why the universe has more matter than antimatter. We lack a quantum theory of gravity that would let us describe black hole singularities and the Big Bang itself. We don't know if our universe is the only one or part of a multiverse. We don't fully understand quantum measurement or why time flows in one direction. These unknowns aren't failures, they're frontiers. Each mystery is an invitation to discovery, a puzzle waiting to be solved. The history of science shows that answering one question typically reveals new questions we hadn't thought to ask. This is progress. Our growing circle of knowledge expands the boundary where we encounter the unknown. How do we know all this? Not through revelation or pure reasoning, but through the scientific method. Making observations, forming hypotheses, making predictions, testing those predictions through experiments and further observations, and refining or discarding theories based on the results. This process has given us a remarkably accurate picture of reality. When we use general relativity's equations to predict the orbits of GPS satellites, they work. When we use quantum mechanics to design computer chips, they function. When we use our understanding of stellar evolution to predict what a star's spectrum should look like, we find what we expect. The universe consistently behaves according to the rules we've discovered. Science is self-correcting. Newton's gravity worked brilliantly for centuries, explaining planetary orbits and allowing us to predict eclipses. But tiny discrepancies eventually emerged, particularly in Mercury's orbit. Einstein's general relativity explained these discrepancies while still giving nearly identical predictions to Newton's theory in most situations. Newton wasn't wrong. His theory was incomplete, an approximation valid in certain regimes. Similarly, Einstein's theory might be an approximation of something deeper we haven't discovered yet. Let's place humanity's brief existence in cosmic perspective. If we compress the universe's 13.8 billion-year history into a single year, with the Big Bang occurring at midnight on January 1st, the Milky Way galaxy forms around March. The solar system and Earth form in late August. The first simple life appears on Earth around mid-September. Complex multicellular life doesn't arise until mid-November. Dinosaurs appear on December 25th and go extinct on December 30th. All of human history, from the first civilizations to the present, occurs in the last minute before midnight on December 31st. We've existed for the tiniest sliver of cosmic time, yet we've managed to decipher much of the universe's story. We've looked back to within moments of the Big Bang and forward to the universe's possible ending trillions of years hence. We've explored scales from subatomic particles to the entire observable universe, 27 orders of magnitude in size. This is a remarkable achievement for beings who evolved to survive on the African savanna. Are we significant or insignificant in this vast universe? Both, perhaps. In terms of physical scale, we're tiny, far smaller than stars or galaxies. Earth is a pale blue dot, as Carl Sagan called it, a mote of dust suspended in a sunbeam. The universe doesn't care about us. It would continue on unchanged if we disappeared tomorrow. Yet we're the universe's way of knowing itself. Through us, the universe has developed consciousness, the ability to observe, to wonder, to understand. We're made of star stuff, as Sagan also said, arranged in such a way that we can figure out where we came from. We can look at light from distant galaxies and calculate their distance, composition, and motion. We can work out what happened in the first second after creation, even though no human was there to witness it. Perhaps there are countless other civilizations scattered among the stars, each contemplating these same questions. Or perhaps we're alone, the only minds in the observable universe capable of understanding it. Either possibility is profound. If we're not alone, we're part of a community of conscious beings stretching across the galaxy. If we are alone, we're uniquely responsible for understanding and preserving knowledge of the cosmos. The scientific exploration of the universe continues with ever more sophisticated tools and techniques. New gravitational wave detectors will reveal black hole and neutron star collisions billions of light-years away. The next generation of space telescopes will image the atmospheres of Earth-like exoplanets, possibly detecting signs of life. Particle accelerators might discover new particles that solve the dark matter mystery. Improved observations of distant supernovae and galaxy clusters will clarify dark energy's nature. Theoretical physicists continue working toward a unified theory that combines quantum mechanics and general relativity, that explains dark matter and dark energy, that reveals why the universe began in a low entropy state. The answers might require entirely new concepts we haven't conceived yet, just as Einstein had to develop new concepts about space and time to formulate general relativity. Young people today will live to see discoveries we can't yet imagine. Some watching this documentary might become the scientists who solve these mysteries. The universe's grandest secrets might be revealed in your lifetime. There's profound beauty in understanding how things work. A sunset is aesthetically beautiful, but it becomes even more beautiful when you understand that you're seeing sunlight scattered by Earth's atmosphere, that the sun is a ball of plasma held together by gravity and powered by nuclear fusion, that the light reaching your eyes began its journey from the sun's core tens of thousands of years ago, bouncing randomly through the sun's interior before bursting free and crossing the void in 8 minutes. The universe doesn't lose its wonder when we explain it. It gains depth. Every galaxy becomes not just a pretty smudge of light, but an island universe of hundreds of billions of stars, likely trillions of planets with its own history stretching back billions of years. Every star becomes a nuclear furnace, creating the elements that make up worlds and life. Every atom becomes a triumph of quantum mechanics, holding together despite the electromagnetic repulsion between protons. Science doesn't diminish beauty or mystery. It reveals deeper layers of both. The more we understand, the more we appreciate how remarkable existence is. This documentary has covered vast territory, but it's only a beginning. Every topic we've discussed could be a documentary itself. The depth of knowledge we've accumulated is enormous, yet it represents just the opening chapters in the universe's story. I encourage you to continue exploring. Read books about astronomy and physics. Watch lectures by scientists. Visit planetariums and science museums. Look up at the night sky and try to spot planets, galaxies, and nebulae. Download astronomy apps that show you what you're looking at. Join amateur astronomy clubs. If you're mathematically inclined, study physics and astronomy. The universe reveals itself most completely through mathematics, the language in which physical laws are written. Einstein once said that the most incomprehensible thing about the universe is that it's comprehensible. The fact that we can understand the cosmos through mathematics is itself a deep mystery. But even without mathematics, you can appreciate the beauty and grandeur of the universe. You can understand the key concepts, visualize how things work, and contemplate the biggest questions. You can experience the sense of wonder that comes from realizing you're part of something unimaginably vast and ancient. The universe is approximately 13.8 billion years old, containing hundreds of billions of galaxies, each with hundreds of billions of stars. It operates according to laws we're still working to fully understand, containing mysteries like dark matter and dark energy that we've only begun to probe. It began in a hot, dense state and has been expanding ever since, creating stars and galaxies, planets and life, complexity and consciousness. You're part of this grand cosmic story. The atoms in your body were forged in stars that exploded long before the Sun and Earth formed. The energy flowing through your body ultimately came from fusion reactions in the Sun's core. Your existence depends on the precise values of fundamental constants, on stars creating heavy elements, on billions of years of evolution, on a chain of events stretching back to the Big Bang. When you look up at the night sky, you're seeing photons that travelled for years, centuries, or millions of years to reach your eyes. You're looking back in time, seeing the universe as it was, not as it is now. You're connected to it all, part of the universe's evolution from simplicity to complexity, from uniformity to diversity, from unconsciousness to consciousness. The universe works according to rules, elegant mathematical laws that govern everything from the smallest quantum fluctuations to the largest galaxy clusters. These rules allow stars to shine, planets to orbit, life to emerge, and minds to contemplate their own origins. We've deciphered many of these rules, and in doing so, we've achieved something extraordinary. We've begun to understand the universe and our place within it. This is how the universe actually works. Through the interplay of matter and energy, forces and fields, space and time, evolving over billions of years according to laws we're still discovering. It's a story more amazing than any fiction, and it's our story. We're made of star stuff, citizens of the cosmos, the universe's way of knowing itself. Thank you for joining me on this journey through space and time, from the Big Bang to the present day and beyond. Keep looking up, keep wondering, keep asking questions. The universe is waiting to be understood, and every one of us can participate in that magnificent quest.